Welcome to this fourth webinar titled Water Quality and Tailings Management in Mining Operations. My name's Martin Draeger. I'm with Water Services and Technologies here in Canada. And I'm here with Rafael Albuquerque as well, located in our Brazil office. Now, a little bit about the company. It was founded in 2017 in Brazil. And there's a gentleman you may be familiar with named Nilson Giger. He's actually the author of Visual ModFlow, world-recognized software application for groundwater flow and contaminant transport modeling. He also authored FlowPath, Airflow of SVE, FlowNet Trans, and really was the visionary behind HydroGeoanalyst and Visual Postos. So we're really happy to have Nilson as our CEO and help guide some of the even more technical areas that we face and our customers face. Now, we also moved outside of mining into other sectors in water resources, whether it was public or private, water and sanitation, and we're helping industrial and energy customers improve their water consumption and understanding their water supplies. Now, with the recent demand on minerals or for energy, green energy, we've now started opening offices in Kazakhstan and also more recently in Canada, where I'm located in Ontario, to really get close to our customers and make sure that we're providing the services required to deliver quickly. Now, about the company, yes, indeed, we do specialize in earth sciences. We have a team of hydrogeologists, hydrologists, and geotechnical experts. And Rafael, being very familiar in leading our aqueous geochemistry group, has a team that will help you with your mining issues as well. We do water audits and have a very large team of digital experts who support the entire organization. Obviously, everything requires data. And so we have this multidisciplinary team that's been helping mines and other organizations with their water, geotechnical, environmental, and data management challenges. Now, to support all of our projects, we do have a professional project management office in place, as well as a group dedicated to technology research and innovation. More recently, due to the fact there was a lack of product out to help us with our field data collection and dynamic water balance, we developed two new products, one visual water balance and the other WST Fielder, which are helping mines understand really what their water balance is in a dynamic way and really help them make better decisions as the operation expands and moves forward. And we do use best-in-class technology to deliver all of our projects. We've got quite a few listed on the bottom here, and it extends beyond that. So we really do lean a lot on technology to make sure that we're delivering projects more efficiently. In terms of the projects, it's a vast range all around water resources. Yes, we do focus a lot on mines, and the customers you see to the right of the screen are all mining customers. But we do offer services around water resources for purely water supply assessment. Obviously, subsurface characterization is a big component of that. Environmental data managed to support all of those projects. And one of the big ones around mining is doing dewatering optimization. And to show examples in terms of quantification, there's three examples here where we've helped a mine save $40 million purely in data management and reporting costs by implementing a software solution and database, basically an enterprise solution to help with those reporting costs for compliance or ESG. We've also helped save time. 97% of a company's time in producing compliance reports. And on the more technical side, we've helped a company save $120 million in operational costs due to our optimization of dewatering. So we're really not just doing technical work. We're actually solving problems that add value to organizations to make sure they stay operationally efficient. So in this webinar, we have a couple goals to achieve. We hope to provide you with insights into the importance of taking a multidisciplinary approach to mine water quality management and decision making. Sometimes we look at problems and we take a very singular lens approach on addressing the solution. Well, Rafael's going to show you why it's important that we look at a multidisciplinary approach to water quality at mines. And also, we really hope that we're going to provide you with the knowledge to help you meet the environmental standards and ESG goals you're setting for yourselves, and actually show you that there is a correlation between reducing costs and risks when you're doing these types of activities around standards and ESG. So I'll give a quick introduction about Rafael. So Rafael is a graduate from Simon Fraser University and Acadia University. He really has expertise in acid neutral mine drainage, diagnosis and prediction, aqueous geochemistry, and numerical modeling. He's got an in-depth knowledge of regional hydrogeological and geochemical assessments and expertise in environmental isotope studies. He carries some certificates in Brazil and was awarded the Outstanding Student Research Award from the Geological Society of America. So, Rafael, without further ado, I leave the floor to you, and we look forward to your talk.
Well, thank you very much, Martin. Thank you all for your interest in this presentation. I hope you enjoy it. It's especially a great pleasure to participate, to actually host this talk, considering the opening of our operations in Canada. So I hope you all enjoy it, right? So why do we care about this, right? So first, as I guess all of us are aware, mining companies are committed to managing water quality and reach their ESG goals. Now, obviously, ESG goals is something very broad, but everything related to water quality, wastewater quality, and not impacting the environment and so forth is an important part of it. And that should be reached while conducting mine operations effectively. Now, within this, one of the challenges faced by the mining industry today at a global scale is to properly manage its wastewater, tailings, and other residues, especially the ones with high potential for chemical load release. And that is the case because contamination events may lead to many negative effects as significant ecological damage, loss of aquatic life, impacts to human health, expensive remediation costs, and damages to the image of the company, and in some cases as the industry as a whole. It's also a challenge because technically it is not something very simple. So the physical and chemical processes leading to environmental contaminations in mine operations are varied and complex, right? But still, it's a challenge that we should face because proper management of effluents and residues at mines involve in-depth technical analysis of relevant chemical reactions and flow systems. So it's complex, but we should face it, right? Just to expand a little bit more on the negative consequences before we talk about the solution. So here I list some examples of consequences of poor water quality and tailings management at a mine site. So we may have issues with failure to meet environmental legislation and regulatory standards. Obviously, this is at a local and national level, right? It depends on the norm at each country and region. Financial losses due to failure and fines, increases in operational costs, high treatment and cleanups expenditures, right? Because well, if you don't have a contamination, you don't have to spend money on this. Damages to the image of the company, and at a global scale, let's say failure or difficulty to meet the ESG goals that the company was set up to achieve. All right. Moving forward on this, if we talk about costs, there are many studies that estimate the cost expenditures that have been involved into managing mine site contaminations and related issues. So I present some examples here. It obviously depends on where in the literature you look at, but usually when we're talking about the industry as a whole, we are talking about something in the order of billions of dollars, right? So very, very, very significant amount of money that is spent globally in terms of attempting to fix contaminations and related issues. Now, talk about money too, but on the good side, and this is very interesting. This is a publication from Canada, from the MEN program. They did a study in the year 2000, and they demonstrated that the actions that they have been taken previously, right, over the past 12, 13 years, previous to that year, in terms of first trying to predict what was going to happen, right? Because we have techniques to predict, for instance, if the mine drainage is going to be acid or neutral, what are the concentrations and so forth. It has uncertainty in it, it's an estimation, but these are techniques that can be applied. So trying to predict what's going to happen, understand these predictions, understand these uncertainties, and trying to proactively act, right? To proactively perform some measurements to prevent these issues of occurring, to prevent contaminations of occurring. It's something that's being demonstrated to save a lot of money. So in this particular example here, if they added all the mine sites surveyed together, there was an investment of 17.5 million Canadian dollars. Well, that's a significant amount of money, no doubt, but depending on what criteria they use, they saved something in between 340 to $1 billion Canadian dollars, right? So they saved at least 20 times the amount of time, the amount of money invested. So yes, to conduct studies, it's an investment there, but there is a financial return to it. So that's very important. And just to mention mine closure, this statistics here, they demonstrate to us that the costs related to water quality and remediation at mine closure is around 10%, 10 to 15%. So you can figure out, you can see that this is a very significant cost at mine closure, right? So obviously all the work should be done also to try to reduce these costs at the end of the mine operation. Talking a little bit about environmental legislation, there are some aspects that are actually simple to understanding from the technical point of view. For instance, if we're talking about wastewater legislation, so usually what we have, let's say there is a location where a mine effluent is being released into a natural receiving stream. So usually the local norm or legislation, obviously this will vary from country to country, is that they will establish a list of parameters that must be met, a list of standards that must be met at the downstream location, right? And depending on the country, they may also establish some standards that may be met, that have to be met at the effluent release location, right? So basically, what we should try to attempt is to, if we have to generate effluent from the mine site, is to generate effluents that have concentrations that are not going to violate these standards, right? And usually we'd like to also monitor upstream in this receiving stream, because there may be cases that anomalous concentrations may be related to external factors like geology, another contamination from a neighboring operation, and so forth, right? So this is something very simple to technically understand, right? Now, it turns out that at a real mine site. Things are not that simple, right? Because what we have is a very complex flow chart of water being pumped by operations and sent to several different uses, effluents being generated at mine dewatering program from tailings facilities, from waste rock piles, from processing plants and so forth. In some locations, 1 or 2 or 3 of these effluents, they mix together before being released. They may be released at different receiving streams and so forth, right? So from the operation and management point of view, it turns out to be something a little bit more complicated than in what we saw in the previous slide. Nonetheless, this is something that needs to be understood. And one of the things that we propose that we do is to do the water balance and the hydrogeochemistry, the aqueous geochemistry, or the chemical load assessment together, right? Because we understand that all these issues, at the end of the day, they need to be looked as a whole, right? In conjunction. And part of that involves establishing indicators and goals, right? So over here, I list a few parameters or a few aspects that may be looked as part of the key performance indicators, so the KPIs, right? And while at a first look, most of these are related to water volume, we'll see that there is a quite an important input from, let's say, water quality and wastewater quality to a proper performance or to improve in performance of these key indicators, right? So again, what we need to do is to look at all of these different aspects in conjunction, as Martin mentioned. So just to give one example, this was one of the bullets in the previous slide, is the reuse of water, right? So from a very simplistic point of view, again, if there is an effluent being generated at a mine site, it will usually go to 1 or 2 destinations. It will either be discharged in the receiving stream, in some receiving body, or it will entirely or partially be reused, right? And reuse, it's something that has a lot of advantages because, first of all, if we're managing to reuse the effluent, then consequently, we are likely discharging less effluent to the natural streams. If we're discharging less effluent to the natural streams, we're decreasing the risks or the possibilities of contaminating the streams, and as a consequence, to violate the given environmental standards that we have at the region that the mine is operating. Also, if we are reusing effluent, we should be having a smaller need to capture or to pump water from the environment, so we reduce freshwater consumption. We also improve our KPIs in ESG metrics, right? If you're consuming, if you're reducing consumption, releasing less effluents and impacting less the environment, consequently, we are improving our KPIs, right? And the other thing is that potentially, this is not always the case, but potentially there are opportunities for cost reductions, right? Because this is not always the case, but in many cases, the requirements, the chemical composition requirements for reuse are not as strict as for discharge to natural systems. Why is that? Because the composition requirements for discharge to natural systems, that in other words are the environmental standards, they're very strict because what the legislation is using, trying to do is to prevent some sort of undesirable damage to the ecological equilibrium, right? Now, to reuse the water, that's often not the case. Obviously, there are some issues sometimes with hardness, specific parameters, and so forth, but that's something that may involve a reduction in costs, because if the requirements are not as strict, treatment costs may be lower, and there is even a potential decrease in operational costs related to pumping systems. So to look for this kind of opportunities is something that we do as part of our consultancy projects. And for this reason, that one of the philosophies that we have as part of our consultancy is to ally water balance and chemical load, right? And to put in in general bullets and why and how do we do this? How do we do this? So first we evaluate in conjunction the water balance and the chemical loads together. So if an effluent come here and join with this one, what are the discharge rates, the volumes, but also what are their concentrations and how do they change when they meet together, if there's a specific reaction taking place or if it's just simple mixing and so forth, right? So that's a diagnosis. As part of this diagnosis, we need to understand what are the inputs to the systems, right? And what are the requirements in terms of water quality, volume, and discharge rate? So that from the point of view of input, and also what are the effluents being generated, let's say, as a result of these water balances and all the reactions and mixing that take place and so forth. So we need to have a clear understanding of their discharge rates and their chemical composition. Also, whenever possible, to look at potential future changes, because we may do this diagnosis as a picture of what's taking place today, but maybe things will change in the future because of operational changes, because of a chemical reaction that is going to evolve, new open pit that's going to open in the mine site and so forth, right? So things change over time, and we should try to assess and estimate how they're going to change, right? And then once we have all of this, including or not the potential future changes, we can establish the potential reuses and the requirements. So what are the requirements in terms of water quality, water chemistry, and discharge rate? And now that we have a mapping of what's being generated and what are the potentials for reuses, we can see if there are any opportunities to match an effluent to a potential reuse. Maybe that can be done directly. Maybe that can be done involving some sort of treatment, but then we can establish based on this analysis what kind of treatment goals are needed, right? And move forward to a treatment study. And then again, eventually evaluate effluents that cannot be reused, right? Once that mapping is done, we can implement and manage operational changes, but most importantly, define and monitor the KPIs and established indicator goals, right? Because what we want to see is that, okay, now we managed to increase, let's say 10% of the reuse, right? We need to know this number. We need to see how this is affecting our KPIs, right? How this is helping the mine operation to be in agreement with environmental laws. How is that helping the company as a whole meet their ESG requirements and so forth, right? So proper monitoring and proper reporting is something that it's part of all this process, right? So that's very interesting. And not only from, let's say, the diagnosis and prediction and proposal of solution part of it, but from the technology part of it, we also develop solutions related to this particular topic that I was talking in the previous slide. One of them is visual water balance. There is a software that is made not for the expert numerical modeler, but for the person in the mine site, because you don't have to be an expert to operate it. It's very intuitive. It's just connecting the dots in the flow chart. And let's say, for instance, if a line is not going from this point to that point, is going from point A to point C instead of point B, you just change that on the plot and it automatically updates the calculations, the KPIs, results, and all the other indicators, right? So this is a very interesting thing. I believe we presented a webinar on this software a few weeks ago. If you're interested, well, you can ask questions at the end, but you can also have a look at our YouTube website for this previous presentation. as I mentioned too, yes. So when we are looking at wastewater management, I think that we should consider a few different steps. Diagnosis is, how are things now? Prediction is, how can things may change over the future? So how can the concentrations and discharge rate change over the future? And even different scenarios, if we do this, with that, and so forth, what are the consequences of that? And in our point of view, the decision making, right, the establishment of solutions should take into consideration these two, the diagnosis, but the potential changes in future, right? Because I've seen, for instance, treatment plants, to talk about something very specific, that were designed, but it did not consider that over the following years, the discharge rate were going to change, right? And now the treatment system is not properly designed anymore. So trying to anticipate how things are going to change, and it's something that we should attempt to do in order to do a proactive management of wastewater. And when we're talking about changes, we're specifically talking about how concentrations and flow rates are going to change, right? How are they now and how they may change in the future. And we should also recognize that there are many different types of effluents being generated at a mine site. And each one of them has their own internal logic on, let's say, the controls to chemical loads, so chemical concentrations and discharge rates, right? So for each one of them, there's specific strategy, there's specific study that may be performed to diagnose and to maybe estimate future changes. So I'm just going to mention a few ones. If we're talking about effluents coming out of drains in tailing dams and piles, well, here from the chemical point of view, we are talking about the classical acid mine drainage or neutral mine drainage prediction and metal release that we're going to talk about a little bit further. But in terms of discharge rate, we are talking about usually hydrogeology, right? So the hydrogeology, the flow system within the structures, where is the flow direction, where is the groundwater level, do we have a saturated and an unsaturated medium in terms of piles, because saturation controls, for instance, oxygen dispersion into the pile and then a chemical reaction. So then again, we're talking about hydrogeology and classic acid and neutral mine drainage prediction. When we're talking about surface, well, so effluents coming out of the surface runoff from tailings dams, then we are talking about hydrology, right? Because the residence time is much shorter. We have specific rain events that may increase the runoffs, increase the discharge rate over a very short period of time. We may have precipitates, right? We have this sort of bright colors there over on the picture that I showed there. So the precipitates, they will impose a stronger control to the chemical composition over, let's say, the primary minerals and so forth. So you see, it's a different logic there. When we're talking about mine dewatering effluents, then we need to combine with the sort of our classic hydrogeological analysis, right? And all the hydrogeological numerical modeling with fee flow and mud flow and so forth, right? So in this case here, I present a plot of a real case that we estimated that the discharge rate from the dewatering program is going to increase by 100 cubic meters an hour. So if this water, if this effluent has high concentrations of sulfates, acid pH, metals, and so forth, that means that, let's say, over the next 6 years, that site will have an additional 100 cubic meters an hour of effluent to treat. So this is something that needs to be taken into consideration, right? So to have this holistic view, in our point of view, is something very important. And then we have effluents coming out of industrial processes like metallurgical plants and beneficiation plants. And then we get back again to the water balance point of view. And we have this on our team, the chemical engineers. They will go into the site and understand what kind of chemical products are applied, what are the beneficiation processes, and how all of these processes may change the effluent composition. Also, potential operational changes in the future, right? So this is to say that each one of them has a different intrinsic logic. So then let's say we generate all of these different effluents, and some of them or all of them are being going to be directed to the environment. Now, another step that should be analyzed is the potential for natural attenuation of these various effluents in receiving streams. So that's another study that we do. And as I mentioned before, this should not be done only at one particular effluent, but a combination of the different effluents from the different origins they're going to be released, right? Because if we want to, let's say, meet regulatory standards at the downstream monitoring point, right? All of the different effluents release need to be okay so that this downstream monitoring point is in accordance to environmental norm, right? So it's something that is done conceptually. There is also numerical modeling done here. So we estimate the potential for environmental non-compliances. We may simulate different scenarios. That's a very interesting one because sometimes the mine site, they want to know that if we do this, if we apply this treatment, if we release this effluent here, if we manage to increase our reuse, what are the consequences? So that's very important. This kind of study helps establish treatment goals because sometimes we may say that, okay, the concentration for a given parameter is at this level here. If we release to the receiving stream, it's not going to be in environmental conformance in the downstream monitoring point. But if we were to decrease this concentration from this level to this level, then we have a better scenario, right? So this delta that we estimate may be used as an input, as a definition to the treatment goals, something that we should do. And then again, this assists in all the decision making related to discharge and treatment options, right? So if I were to add all of this in a very simple diagram, we have the effluent's chemical load. That's something that we need to understand, right? So this is what the operations generate. Obviously, we can look at potential operations change, but let's say that's what they generate. We can look at reuse opportunities. And at the end of the day, there's always some effluent, or usually some effluent that is going to have to be released. So for this effluent that is going to be released, you need to evaluate what is the attenuation capacity or the attenuation capacity of the potential receiving streams. And hopefully by assessing these ones, we can reach the treatment goals. Now, it may be the case that the treatment goals may lead, let's say, to a treatment system that is too expensive for the operations. So we may need to reiterate this entire analysis, right? So this diagram is to show that at the end of the day, in our point of view, decision-making effluent management should take into consideration all of these different aspects in conjunction and in an interactive form, right? Talking about treatment goals, we also have chemical engineers that do consultancy in mine effluent treatment. This is just one slide to summarize the service. We had a webinar in Portuguese on this topic recently. We should do one in English in the near future. So first of all, we have to look at the integrated solutions, which is to look at all of these that we just said. So what are the opportunities for reduce effluent discharge in concentrations and reduce treatment complexity and costs? But at the end of the day, let's say some treatment is going to be needed. Then we can perform the entire scope of laboratory analysis, treatability, trade-off studies, conceptual designs, and supervision of basic treatment systems, right? So sort of like the classical treatment consultancy. But we can also ally to that numerical modeling, right? So we're going to talk briefly about numerical modeling, but that's something that we've been working on, doing numerical modeling, thermodynamic and kinetic reactions to support the effluent treatment consulting work. And based on that, we propose the improvements. Now, moving to tailings, but obviously from the geochemistry point of view, due to many of the recent events that took place, especially here in Brazil, there are many standards that are being put out. I'm going to mention one of them. So the global industry standard for tailings management. This is a standard that takes into consideration several different topics like affected communities and so forth. But obviously this is focused on geotechnics, right? Because this was developed after the dam disasters here in Brazil. So the technical part is focused on geotechnics. Now, one thing that it's very interesting to note that on topic 2, principle 2, so the first principle is focused on affected communities, obviously, people first. But the very second principle talks about integrated knowledge base, right? So it establishes that the mining companies assigned to it should develop and maintain an interdisciplinary knowledge base to support safe tailings management throughout the tailings facility life cycle and closure, right? So develop and document knowledge using approaches aligned with international best practices. But on what topics? And on requirement 2.2, we see that it's listed geochemistry, hydrology, and hydrogeology, surface and groundwater flow and quality, right? So we see that the GISTM is looking not only as the tailings safety in terms of geotechnical aspects, but also in terms of their potential chemical impacts to the environment, right? So this is a relatively recent standard, and it's interesting that it points out to that. And it mentions international best practices without being too specific about it. So I'd just like to mention that in terms of international best practices, when we're talking about mine drainages, there are some of them, like the AMITA, the GUARD Guide, and the MEND. The MEND is the Canadian one. And they establish different sampling methodologies, anyhow, the whole scope, right? Different laboratory analysis that can be performed, the general scope of the studies, numerical modeling, and so forth, right? So there is a whole scope that is already being established and in our point of view can be used to meet, for instance, GISTM goals. And to summarize, regarding their principles and requirements, there are two crucial points that arise for consideration. So to build the knowledge base, it's imperative to characterize the material intended for deposition in the structures, right? Because we're trying to estimate what's going to happen, right? Obviously, if the structure already exists, we can sample the material there. But if the structure still hasn't been in place, we should try to characterize and estimate the potential chemical load release before the installation of the structure. And based on that, to anticipate, right, to estimate the conditions and the effluent composition and quality at the discharge point of the structures so that, as I mentioned, proactive decision making can be made to try to control this before it happens. So very briefly on how this is done. This will be a brief summary. So we understand that this kind of work on tailings and waste rock should be started with a geological setting, right? Because tailings and waste rock, it's obviously there is chemical products that are added to tailings, but a good amount of it is minerals, right? So we need to understand what kind of mineral assemblage are there and where do they come from, and obviously what it's known about these minerals. There's quite a lot of work that associate economic geology with potential chemical load release in terms of concentrations and which parameters, right? And this should also be taken into consideration in terms of establishing our sampling program, right? So this is to say that there is already a lot of interesting and relevant information available before the actual environmental work is done, and this should be properly assessed. Then we go to sampling. Now, there's a lot to be talked in sampling, so we need to figure out or to decide. And again, this is always based on the objective, right? The objective needs to be very clear. What kind of samples are we going to take? So we're talking about drill cores. We're talking about tailings leaving the chemical plant, tailings already deposited in the tailings storage facilities, waste rock piles. Anyhow, so what kind of sample types are we looking at taking? And each one of them has advantages and disadvantages, right? Then the number of samples, the representative amount of samples. If we, what are the criteria of establishing what is representative amount of samples, conceptual, statistical, and so forth, right? And then the methodologies, the analytical methodologies are going to be applied because they also imply on costs, which may reduce the number of samples that may be taken, and also the volume of samples that need to be taken, right? Which again may imply a limit to the number of samples. And then when we are talking about predicting future concentrations, we need to take into consideration the site characterization conceptual model, right? So what's our conceptual understanding of the chemical and physical and processes taking place there and the flow system, and a combination usually of laboratory testing on the samples that we collected and numerical modeling. Why laboratory testing and numerical modeling? Because there are many laboratory tests that stimulate the reaction, so we can use them to see what kind of solution compositions come out of them, right? So that's an estimation. But these have limitations, right? Because a test being performed in the laboratory is different. That's something that has, let's say, 100 meters high, like pile or tailings facility that is being subject to seasonal controls and so forth, right? Numerical modeling can be done to simulate these environmental conditions, right? Now, also numerical modeling has limitations. So our vision is that these estimations should preferably be done with an intelligent combination of laboratory testing and numerical modeling. When talking about laboratory testing, there are a lot of different methods that can be performed. Some of them are cheap, some of them are expensive. Each one of them have a specific objective. Each one of them cover a specific part of the information that we need and will not cover another part and so forth. I'm not going to go into great detail into this, but this is to say that the selection of what methods are going to be applied given the objectives of the work, it's something that it's part of the work that we do in our consultancy work, and the whole interaction with the laboratory, understanding what are the laboratories available in the given regions, what are the capabilities, if they have the given quality to fulfill the requirements that we need, and so forth, right? So there's we could have a whole webinar on laboratory testing. Numerical model, as I said, is a complementary of that. We need to understand the model is a simplification of reality. So even if we do an excellent model, there are limitations to it, right? And a numerical model, it's a consequence of the conceptual model, right? So we need good data to support a conceptual model, and we need people working on a conceptual model that have experience and they can make, let's say, good use out of that data. The classic software that we use for numerical model is FreakC, as it's mentioned here, and that's one of the softwares that we use. Why develop a numerical model? So again, it's used especially to estimate composition of effluent and water quality, acid drainage, nutrient drainage, effluent composition, and so forth. It may be used to validate conceptual understandings and hypotheses. And this is something very interesting because sometimes we think we understood well why a given concentration is elevated of a given parameter, but when we run the model, we don't reach the result that we're thinking, right? And that forces us to go back to the concepts and revise them, right? So that's always a very interesting thing. And perform complex calculations, simulate different scenarios, analyze sensitivity and uncertainty, estimate environmental aspects that cannot be reproduced in laboratory testings, and simulate the scaling factor, right? This transfer from a laboratory scale to a field scale. And this slide is just to show that just something specifics. There are a lot of decisions that go into consideration when performing numerical models. So one of the issues is if the model is going to be pure equilibrium thermodynamics, or if it's going to take into consideration kinetics. So this is an example that we did here, that we have a completely different result if we do pure thermodynamics equilibrium or if we add kinetics to it, because without kinetics, the model will assume that everything is going to happen instantly, right? Which is usually not the case. So we've been putting a lot of effort into kinetics, numerical modeling for my drainages and other usages. And more of that, I'd like to mention that our very next webinar will be solely on advanced aqueous geochemical numerical modeling, which will be in 2 weeks' time on April 24th. If you're interested in watching this webinar, please click on the link. I think Alan's posting there, and you can sign up to this webinar. This is going to be a very interesting one. So just to close my presentation, I hope I managed to show you that managing water quality and, let's say, chemical loads released from tailings has a lot to do with ecogeochemistry. And myself as a geochemist, I could spend the entire day talking to all of you about it. But we have to recognize that other areas of knowledge come into play. And that's why we have this vision of integrated solutions and bringing the different areas of knowledge, the different areas of expertise of water service and technologies into the diagnosis and the solutions of challenges that our clients bring to us, right? So I think that's it. I'd like to thank you all again for watching this presentation. I hope you enjoyed. And please follow us on our social media.